Hello students, welcome to video lesson 7.5. This is actually our last video in chapter 7. It's a pretty short chapter and we did skip one section. We're not doing section 7.4. So this is it for chapter 7. We will take a quiz at the end of the week. And in this video we're going to talk about a few extra theorems that allow us to set up proportions and find missing lengths and missing distances and things in two triangles. Okay, so we have two theorems to go through and then one sort of extra application of one of those theorems. And the first one, your book gives kind of a fun name to it. It's called the side splitter theorem. Apparently it's a hilarious joke or something. Right, side splitter would, because you're laughing so hard. Anyway, it says if you draw a parallel line to one of the sides of a triangle. Okay, so in this case, they have it sort of parallel to the base here, like this bottom side, but it could be any parallel line in a triangle, that's parallel to one of the sides. It cuts the other two sides into lengths that make equal ratios. Okay, so here's what that means. If I draw RS across this triangle here, that's parallel to XY. If I know that they're parallel, then QR, this distance, and XR, or they go XR and RQ, those two lengths and these two lengths, QS and SY, they make equal ratios. Okay, so anytime you have a parallel line going across a triangle, we have equal ratios for the pieces that the other two sides are cut into. All right. So if we look, for example, at something like this, here they give us a picture of a triangle. They give us a parallel segment in the triangle to one of the sides, and they want us to find the value of A. So we're going to have to set up a proportion and do a little bit of algebra here. Okay, so this is going to take us back basically to section 7.1 when we were solving proportions with some algebra. Okay, so the good news is, especially if the triangle is arranged sort of like this, where the parallel side, the parallel segment is parallel to the base, it really sets up our proportion for us just by looking at this picture. Okay, so the proportion I can set up is A over A plus 4 is equal to 12 over 18. Okay. And then, of course, I will do my cross multiplication, and one's going to say 18a, the other's going to say 12a, 12 times a, 12 times 4 is 48. So I end up with this equation that then I can solve for the value of a by simply moving all the a's to the same side, minusing 12a on both sides there. This becomes 6a equals 48. Divide by 6, I get A is equal to 8. Okay, so when we have a parallel segment to a side, we can set up a proportion for the pieces that the other sides are cut into, and then we can use that to solve for missing values, for variables, for missing lengths, etc. Okay, our extension of this theorem is actually, your book calls it a corollary to this theorem, basically something we get in addition to this. And that is basically the fact that this picture does not have to be a triangle. Okay, so this picture shows me 3 parallel lines and 2 transversals. Okay, 3 parallel lines, 2 transversals. I've got parallel line A, B, and C, and then I've got these 2 transversals that are cutting across here. It's essentially, you guys, right, we've sort of taken the triangle and we've opened up the top, right, so that the top doesn't come together and meet at a point, but there's space. So there's another parallel line there at the top. And this also creates equal ratios. I need to locate sort of the pieces. So one piece goes from A to B right there. Okay, and that is makes a ratio with B to C. Okay, so the 2 sides on the left, or the 2 pieces on the left in this case, make an equal ratio with the two pieces on the right. So WX then is also making a ratio with XY. Okay, and so the pieces on the left as a ratio are equal to the pieces on the right as a ratio, as long as those three sides are parallel. All right, so again, this is just an extension of the side splitter theorem, taking the top of that triangle and just opening it up. All right, so our other theorem that will allow us to make proportions in triangles is something called the angle bisector theorem, or the triangle angle bisector theorem. Sometimes I shorten this to TAB, triangle angle bisector theorem. Okay, so you can call it the TAB theorem in your notes if you want to. Basically what this says is, if I draw the bisector of any angle in a triangle, so in this case I've drawn the bisector for angle A, right? I can see that that ray that's extending through this other side is cutting angle A into two congruent pieces, so it's a bisector. That bisector cuts the opposite side of the triangle into two pieces that are equal ratio with the other two sides. Right? So here's what that means. When I draw the bisector, it cuts this bottom side into two pieces, right? CD and then DB. If I make a ratio out of those two pieces, CD and DB, that is the same ratio as the other two sides of the triangle, okay? So AC and AB make the same ratio, okay? Now, it is important when we do this to set it up in the correct way. So you sort of have two options, okay, when you see something like this. We can go left over right and left over right, okay? So in this case, A comes down, the left-hand side is CD, the right-hand side is DB. The left-hand side of the triangle is AC, the right-hand side is AB. So we go left over right, left over right. Okay, it's also okay, just from our properties of proportions that we looked at back in 7.1, right, to switch these two things around, and we can go left over left and right over right, as long as we go, maybe it's the side lengths on the top and the pieces of that third side on the bottom, right? Or it could be the other way around. It doesn't really matter. There's a lot of ways to set up these proportions. I think it's probably easiest just to go left, right, but you don't necessarily have to do it that way. You can go left over left, right over right, as long as they sort of match up, okay? So if we look at an example of this, I have this triangle here, and I notice that this line cuts this top angle into two equal pieces, so that is an angle bisector. So I know that that cuts this bottom side into two pieces that make the same ratio as the other two sides of the triangle. And again, because I went 9.6 over 16, I'm going to go y over 24. But it's also okay if it makes more sense to you in this picture to go y over 9.6 is equal to 24 over 16. That's perfectly fine. You'll come up with the same answer doing it either way. This is a simple application of solving proportions. This is one we could use the fish method if we sort of remember that. 24 times 9.6 divided by 16. And if we punch that in on our calculator here, 24 times 9.6 divided by 16, we get that y is equal to 14.4. Okay, so just setting up these proportions from the two pieces of the side that gets cut by that angle bisector, and then making a proportion with the side lengths, we can solve for missing sides of the triangle, we can solve for missing lengths, missing pieces, figure out distances, and things like that, okay? If you have any questions about either of these theorems or sort of that extension of the side splitter theorem, do please reach out to me. Otherwise, that's all I have for you. We will do some review coming up here and then take a quiz, and that'll be the end of chapter 7. So If you need anything, let me know. Otherwise, that's all I have for you, and we will talk to you soon.